Good afternoon, everybody. My name is Trevor Spence, CEO and co-founder of OsseoMimetic. So we discovered last night we had some Apple to PC conversion problems. So we had to re-up here, and I got some good feedback as well from the team. So we are a spinal fusion device company aiming to set a new standard in spinal fusion with proprietary microgroove, parallel microgroove technology. So spinal fusion, for those that don't know what this is a surgical procedure where we, let's see, this doesn't quite work, but we insert a surgical device between two vertebrae in the spine, and we want the bone to grow around and onto the device to create a stable spinal area to alleviate pain in patients that have spinal conditions. What's important here is to get direct bone attachment to that device and to get that stable device in between the spine. There's basically two types of materials typically that are used in the industry for spinal fusions. One is a material called PEEK. It's polyether ether ketone. It's a bioinert material. It has a rigidity similar to that of bone, which is why it's used for orthopedic implants. And what this does is it shares the load around the implant, which is necessary for to support healthy bone growth and to regenerate bone, because bone actually needs the mechanical stress to regenerate. Titanium, on the other hand, great material to get bone attachment for the short term, but over the long term, it has the propensity or potential to be too strong, and it's a process called stress shielding, where you can get bone recession around the implant. And not only is it right around the implant, but it can extend to the adjacent vertebrae or other joints. PEEK, on the other hand, doesn't get great biocompatibility with bone or bone attachment. And here what I'm showing is fibroblast cells, soft tissue cells on flat PEEK. So this is a PEEK device, which is these ridges here, they're on a macro scale. So we would still consider this a flat PEEK device because the cells are still reading a flat surface. But what we're showing is the cells are spread and they're in the proliferating state, which means that they just want to coat the surface and have soft tissue covering the entire surface. Now, this is not good because we want bone to grow on that surface. And what we're showing here on the right-hand side is a device in between two vertebrae with a layer of fibrous tissue encapsulation or scar tissue that blocks that bone growth onto the device itself. So there are current devices that are in the market, but the negative outcomes include long healing times, anywhere from like 18 to 24 weeks, post-surgical chronic dull pain, which is known as pseudoarthritis. And a lot of this is due to the fact of not getting that direct bone attachment to that device. And you can get device loosening, which causes pain to the patient. And then long-term bone recession, which I talked about, due to the high rigidity of titanium. So there's no product in the market that has a simple and cost-effective solution that addresses all of these issues. On top of that, the pain that patients feel, and there's a potential for infection, leads to over $2 billion of revision surgeries per year. So that means they get explanted and a new device has to go back in. And as a patient, I mean, obviously that's really painful and you want to avoid this as much as possible. So we patented a spinal fusion device with microgroove technology. And what this does is we get direct bone attachment onto the surface. And by the microgrooves on the far right-hand side, so we got zoomed in here with stem cells that kind of plop right in the center of these microgrooves. And what that does is it holds these cells into what's called a differentiated state. That means they can excrete the extracellular matrix, which eventually will mineralize and lead to regenerated bone. On top of that, cells migrate along the direction of these microgrooves. So we call that contact guidance. So we have the parallel microgrooves going from top down and bottom up so that we can reduce the healing time in the patient by growing bone from either side and also through the material or through the center. The image on the left here, the micrograph on the left, are fibroblasts, the soft tissue cells. And if you can remember, compared to the last slide, where they're flat and spreading, here you can see they're clearly in the direction of these microgrooves. They don't like having to bridge over. It's like jumping across a canyon for these guys. So they don't like going across. So we have the orientation of the microgrooves also plays a part to inhibit or discourage scar tissue encapsulation across the top of the microgrooves where we want bone to have direct bone apposition. So overall, we're seeking to accelerate healing by 4 to 6 weeks with this microgroove design. We can reduce pain and revisions by having this design by inhibiting that scar tissue ingrowth for less revisions, and then also covering the entire implant with bone. Something that's not done for other PEEK devices. Because it's made out of PEEK, we expect that it would stabilize the spine over the long term because it shares that load and we get that mechanical stability and that bone regrowth. And overall, by having less revisions, we can save money to patients, hospitals, and in the industry in general. So there are several players in this market. So there's a lot going on here. But what I want to point out, so let's see, Medtronic, ZimV, which is prior to Zimmer Biomet, Stryker, all the big players have spinal fusion devices. What makes OsseoMimetic stand out is its cost-effective and simple design to get the bone ingrowth and increase that or decrease the healing time, increase the speed for recovery. And we can do that without compromising the material strength. So for example, a 3D printed PEEK spinal cage, which just got through the FDA. Now that's not going to have near the compression strength what a bulk plastic material is going to have, which has 2 decades of use behind it. And then also, we don't compromise the radio transparency. So when you take an X-ray, you want to see where that bone regenerated. Using a plastic material, X-rays go right through, you don't see it. You can see that bone where it's regenerated. We plan to implement a direct sales model, selling directly to hospitals, surgeons, and spinal clinics, starting with first a cervical device, and then a lumbar device. That's typically the order that these happen in the industry. And then we would scale up using a distribution model. I wanted to note a couple of liquidity outcomes. First being Titan Spine. They were a titanium spinal fusion device manufacturer that used a roughened surface of titanium. They were acquired by Medtronic. And Vertera Spine is more closely related. They're a PEEK spinal fusion company that developed a porous PEEK surface around the same time that I did the microgroove design. And they were later acquired by Nuvasive, which is right down the street here on the 5, for an undisclosed amount. But what they did is they got through the FDA, created a cervical device. They were working on the lumbar, and that's when they got acquired. So we're asking $400,000 for a pre-seed investment, and what this money would be used for is to create more robust data, so including an animal study, and then we would transition to using a second or a third round to get money to go through the FDA through a 510K process. There's several milestones, milestone 1 and 2 being that animal study and creating that more robust data. This is where we expect that we would have, even just with one of these milestones, create enough information to present at the conferences so that there's like 3 major ones just in each year for orthopedic and spine, that it would generate a lot of interest in the industry. I've seen this happen with less data than what I propose here, and people get excited about this stuff at these shows. And then we transition to milestones 3, 4, and 5. This is like getting through the FDA product development for the cervical device, and then launching by 2026 with the cervical, and having the lumbar in development, and then being cash flow positive by 2027. The market is large just in the US alone, with $1.1 billion for PEEK devices and over 450,000 spinal fusion surgeries each year, which equates to over 1 million devices that are actually used each year in the United States. Compounded annual growth rate is 7.4% up through 2033 for PEEK devices. We have key partnerships and advisors for business operations, device design. These are spinal device employees, regulatory, getting through the FDA, and then also for marketing. And I wanted to mention here, we are looking for an orthopedic, possibly a surgeon or somebody that's an expert in orthopedic to be an advisor as well. Our management team is comprised of me and Dr. John Ritchie. So I've worked in the plastics industry for over 20 years. I studied under Dr. John Ritchie in biomaterials and the tissue interface with bone. Dr. Ritchie is an expert in this area and was a co-founder for a medical device company that was later bought by BioHorizons, a top 5 dental implant company in the world. One thing I want to note is the technology we're using here is similar technology that he devised and sold over 20 years ago that's used at BioHorizons. Now that's on titanium. What I did is I applied it to plastic and put it in the form of a spinal device. So we are really confident in the outcome of how this is going to work. This is the traction. We have the patent that was granted in 2022. We've completed cell research studies, and we have a regulatory strategy to get through the FDA. We expect to launch the cervical device in 2026, lumbar 2027, and have much larger gains by 2030 with only a small percentage of the market share. And that's it. Try to get through as fast as possible. Thank you. I appreciate the opportunity to share my vision. Thanks to Aquillius for having me here today and for you guys listening. If you're interested in talking, please reach out. Love to hear from you.
Thank you very much. Got a couple of questions. First of all, will this require any change in either surgical procedure or surgical tools, products, et cetera, and what type of training for them? And the other thing, just as a comment, I should just put a little QR code when you're doing a live presentation, just easy for us to kind of keep contact with you, et cetera.
Oh,
so,
great,
thank
great,
you.
great feedback. So we do expect the instrumentation to be the same, and that is part of the development process. So we do need to make the instruments with the spinal fusion device itself, but it's pretty standard in the industry to do that. And the consultants that I have from the engineering side, they're experts in that area.
Does your animal studies also include in human studies, and also share what is your strategy around animal and human studies? The timeline and the cost seem, I wanted to understand the context of that with respect to your timeline and cost estimates.
Sure. So first, as far as the animal studies go, we would start with a rabbit model. That's what's been done in the past that we can kind of follow the similar procedure. We don't anticipate doing any in-human studies. We'll follow a 510K process to get through the FDA. If we need to, after having the rabbit study, we may go to a sheep model because that's where we can have the closest thing to having a spinal implant and do that in a sheep. We may or may not need that. But I budgeted for it in that amount, the $5 million, and same with $400,000. That's for the rabbit study and some more in vitro diagnostics as well. Does that answer everything? Okay. Oh, that's a great question. So to see the osteocytes would be probably closer to a couple months, like eight weeks or so in the animal study. But we would do these out probably up to 3 months in the animal study. The cell studies were the original, but those can be done like pretty quickly.